So, I guess maybe like Professor Clark, would you be able to introduce yourself a little bit about what you do and all the research that you have done in the past?
Yes, I'd be happy to do that. And please do feel free to interrupt me at any point if you need me to expand on something or I'm going on for too long and or you have questions.
Yeah, okay, thank you.
Okay. So I was born and brought up in England at the city of Cambridge.
Mm,
And the city of Cambridge is probably most famous for this wonderful King's College Chapel, which was built 500 years ago. So people, when they hear about Cambridge, that's probably the first thing that they think about if they've been there. Anyway, I went to school for 12 years at the Perse School,
mhm.
which is it was a wonderful school. I was there 4 years in the prep school and then 8 years in the senior school, and that's where I learned so much. And it is close to King's College Chapel. This is now a sort of a map of the city of Cambridge,
Mhm.
and King's College Chapel is up here. And along here is Free School Lane, right in the middle of Cambridge. And this played a very important role in my life for reasons that I will now explain. I mentioned that I went to the Perth School, and it was founded in 1615 by Stephen Perse, and it was one of the first free schools in Cambridge, or maybe the first one in Cambridge, where they would educate people, boys from poor families at no cost. And the lane it was built on originally was called Free School Lane. So that's the
Oh, wow.
origin of that name. Now,
Yeah.
subsequently, by the time I got there, a few centuries later, it had moved somewhere else. But
Mhm.
anyway, that's an important point. Next thing is that also on Free School Lane was my grandfather's picture framing shop, where he
Wow.
framed pictures. That was, the way he earned his living. And you can see that it's on a lane. It's not, the preschool lane is a lane. It's not something you can drive along.
I see.
And the Perth School was founded here, and there was my grandfather's shop. And roughly speaking, they're just over 100 yards apart.
I know, that's pretty close.
Yes, that's pretty close. So I was an undergraduate at the University of Cambridge. And of course, after that, I had to decide what to do next, in particular, where to go to do research. And so I spent a lot of time pondering this and going to various research labs, both in other cities and also in the city of Cambridge.
Mm.
And in the end, I decided that I was going to go to the Royal Society Mond Laboratory.
Oh, wow.
And the reason I was going to go there is because of that. That the Mond Lab was between the Perth founding and my grandfather's shop.
Wow.
And so that's why I ended up going to the Mond. It was the best
Like,
decision I ever made in my life. Okay.
yeah, that's like the perfect spot.
Yes, yeah. So it was preordained. I mean, somehow it was all in the stars that that's
Mhm.
where I would go to. Okay, so I sort of, there were various people, thesis advisors, professors I could work for, and one of them who I thought was a very interesting person was called Brian Pippard, who was also a very famous guy. And he said, I have this one thesis project that I think is the most interesting and potentially important, but it's going to require us to measure voltages of a billionth of a volt or less. And at
Yeah.
the time, the state of the art was 1,000 times larger than that. And he said, I have to be honest, he said, I don't know how to do this. but he said, if you think you can figure it out in your first 3 months of working for me, then it will be wonderful. But if not, I'll give you something else to do. So I started to work on thinking about this. And after the first month or so, I thought, this isn't going to be very easy. But one day, Brian Josephson gave a seminar. And there's a picture of Brian giving his talk. And of course, on those days, you wrote in chalk on a blackboard.
Yeah.
And this is a quick summary of what he said. Now, squids are based on superconductivity. Superconductivity is a phenomenon in metals that lose all their electrical resistance. And they are driven by a theory later invented by Bardeen, Cooper, and Schrieffer. And the basic point is that the electrons in the metal are paired together in what's called Cooper pairs. And they have a charge of 2 electrons. And all the current in superconductors, I've tried to show here, is carried by these Cooper pairs. And it's a low temperature phenomenon. I mean, everything I'm going to tell you about is done at very low temperatures.
Yeah.
Although today there are high temperature superconductors. So that's the first point. This may seem like a very unimportant point, but superconductivity obeys quantum mechanics. And if you have a closed loop of superconductor and it has some magnetic flux trapped in it, which of course generates a magnetic field,
yes,
then it's quantized. It's quantized in units as what's called the flux quantum.
Oh, okay.
And so that's we're getting towards the origin of the name squid.
Okay.
And then Brian explained his Josephson effect, which he never called. He never called it himself the Josephson effect or talked about Josephson tunneling. Very briefly, what he explained was that these Cooper pairs that carry the current, if you put an insulating barrier in their way, they can go through it by what's called tunneling, which is a very, very important effect in quantum mechanics. And he explained this in some detail, and it's all explained by large numbers of equations using lots of calculus. And I mean, people write books, as I'll show you in a minute, about all this, and it's all calculus, okay? But about a year later, he predicted this in 1962, and it was observed in Bell Labs in New Jersey in 1963 by these guys, Anderson and Rao. And what they showed was that if you make one of these devices and you cool it down and you pass a current through it, at very low currents, the no voltage is developed, and then it makes a transition to a voltage regime.
Oh, I see.
So that's going to be, it's going to drive more science than you could imagine.
Yeah.
And we'll get to that. So finally, what is a squid? Well, the squid consists of a superconducting loop, but these 2 X's mark Josephson junctions. So there are 2 of them on this loop.
I see.
And by the way, this is, I don't know if I can get this. Oh, yes, I can. Oh, no, I can't get that out of the way. That's too bad. Anyway, because I've lost the title. But anyway.
Oh, okay. I see the title on my end.
Okay, good. All right, that's good. Yeah. So it turns out now that if you make one of these loops and cool it down, again, you get this 0 voltage regime, and then it becomes a resistor. But if you apply a magnetic field to the loop, then you find that the voltage across the loop oscillates as you increase the magnetic field. And the distance between these 2 peaks is this flux quantum that I just introduced.
I see.
Yeah. And that is why it's called a superconducting quantum interference effect device, SQUID.
Mm.
So this phenomenon was seen many decades before in optical experiments, but it's called interference. But that's why it's called a superconducting quantum interference defect.
I
And
see.
it's
Yeah.
because of the flux quantum.
Mhm.
So that's the origin of all this stuff. Whoops. Whoops. Hold on a second. Yeah. Okay. So the very next morning after Brian Josephson gave his talk, Brian Pippard came into my lab with the biggest smile on his face. And he said, John, how would you like a voltmeter with a resolution of 2 times 10 to the minus 15 volts in 1 second? And that sentence defined my career.
Wow.
Everything I've done since then for the last half century or more came out of that one sentence.
Wow. I see.
And I won't sort of try to explain exactly, what the basic idea was, but I had to make a squid. Now, in those days, that wasn't so easy because all the technology we have today, I'll talk briefly about, didn't exist then, and I had to figure out how to make one. But one of my fellow graduate students at tea time, every day we had tea together, and so someone else in the same lab, he said, he told me about solder blobs. You probably know what solder is.
Yes.
And a piece of niobium wire. I said, why don't you put a blob of solder on a piece of niobium wire and see what happens? And before dinner that night, I had Josephson tunneling. So
Wow.
this was tea time. He suggested this, and I made one, and I happened to have some helium, and I put it in there. And within a couple of hours, I had Josephson tunneling. And
That's really interesting.
yeah, I was so excited. And so was Brian Pippard.
Mhm.
And next morning, he came into the lab. He said, how's it going? I said, look, I showed him the device, and I showed him the data. And he looked at it, and he said, it looks as though a slug crawled through the window last night and expired on your desk. And that's a slug.
Yeah.
So that was it. Now, I still had to make a squid out of this. I had to have interference. But what I found was, and again, I won't go into the details of this, but what I found was that if you pass a current along this piece of niobium wire, then the voltage between the wire and the solder would oscillate, as in a
Oh,
squid.
wow. Voltage between the wire and the solder would oscillate.
Yeah, just as in a squid. So this thing, although you would never guess in a million years, it behaves as a squid.
Wow.
And so, well, 2 things. First of all, we had to decide what to call it, but Brian had already made up the name, and it was the slug. So it was a superconducting, low inductance, undulatory galvanometer.
Wow.
A
That's really cool.
galvanometer is something that measures current, and it undulates up and down. So that's the slug.
Yeah.
And I made this into a voltmeter by connecting a resistance in series, and I got to a voltage rather easily of 10 to the minus 14 volts or 10 femtovolts, within a small factor of what Brian had wanted.
Yeah.
And the
Wow.
thing is, this was 5 orders of magnitude better than the state of the art at the time.
Yeah.
Okay, so so that's the story of my life, of my scientific career. But just to sort of finish up this discussion, today's devices are made out of thin films of superconductor, and they're deposited on silicon wafers or whatever, in incredibly small sizes these days. And I won't go through the details of this, but this is today's technology in a million different varieties.
Oh, wow.
So
And the Josephson junction is the super small part of the squid with the input
yes,
coil.
it's right here. I've blown up the region here, and the Josephson junctions are here and here.
Oh, wow.
Yeah,
That is really small.
yeah. Well, they're much smaller today, but anyway.
Yeah.
And this is sort of this took a long time. This is 1981 before people really had the technology to make thin film devices.
Yeah.
So anyway, after the slug, I had to decide what to do next, and I got my PhD at the end of 1967, and I had an invitation to go to the University of California, Berkeley.
Mm.
And so I got on a plane and I went to Berkeley, and I planned to be here for a year.
Mm-hmm.
And it turns out that after I'd been a postdoc for a year, they invited me to become an assistant professor. And so I joined the faculty, and that's where I've been ever since. And, and I retired in 2010 after teaching for 41 years, but I'm still
Wow.
here. And I'm what's called a professor of the graduate school. And that means that I don't teach anymore, but I'm allowed to do research.
I
So,
see. Yeah.
so that's where we've got to right now, and that's already taken a long time. Okay. So you'll ask it?
Oh, yeah.
Yes.
Okay. So, what are magnetometers and how are squids related to them?
Right. Yes. Good. So magnetometers, as you might expect, measure magnetic field, and there are many, many different types of magnetometer, not just squids, but lots of other ones. And many of them will just measure a static field. And for example, the Earth's field is roughly 50 microtesla, or 5 × 10⁻⁵ Tesla. So that's the Earth's field. And there are many standard magnetometers that will measure that quite accurately. But the squid is usually used as a magnetometer with additional circuitry, but it measures changes in magnetic field. It doesn't measure the static field.
Yeah.
And the resolution that we now have, in fact, it's even better than this, is 10⁻⁵ Tesla.
Mm.
That is a thousandth of a billionth of a Tesla.
Yeah.
So it's a tiny, tiny fraction of the Earth's magnetic field.
Wow.
And really all the squids that are used today in all these different applications measure the equivalent of something like that. Or if they're a voltmeter, they measure in an equivalent voltage.
Mm-hmm. Wow.
That's how these are related.
Yeah.
So maybe we should go on to your next question.
Okay.
Some
Do you
of
think
some
you
of my
could,
research.
talk to us about some of the research you've done in the past?
Yes. Okay.
Yeah.
Again, first, as a sort of general comment, I've done, I don't know, hundreds of experiments in my career. I'm very much an experimentalist. I mean, sometimes I work things out, but I'm basically an experimentalist.
Mm-hmm.
And I've picked 3 very different topics just to sort of illustrate them. But most of my research is really done on more fundamental experiments on what they call solid state physics or condensed matter physics. But I picked 3 other things.
Okay.
So first thing is that I have a lot of colleagues at Berkeley who work on cosmology and astronomy. And one thing I learned from them a long time ago is that our universe that we all are part of is a very bizarre situation. And we know more or less that the universe consists of neutrinos, which is a fundamental particle. We needn't worry about it. What's called baryons, which is ordinary matter. We're baryons.
Oh, wow.
The Earth is made of baryons. Everything in the universe that's solid is made of baryons.
I see.
Okay. However, 95% of the universe is unknown. And so two of the big challenges today are two different things. One is something called cold dark matter. Now, what the people have figured out who work on cosmology is that there's a lot of what we call matter. Baryon is in the ordinary matter. There's a lot of matter, about 27% of the universe, and we have no clue what it is. Mm. 2/3 of the mass of the universe is what they call dark energy. And you know that you can relate energy to mass through a famous MC² equation. So I have sort of been involved in working on both of these because it turns out we could help a lot with squids. So the first of these is cold dark matter that I just talked about. And I've called it the hunt for the axion. So one highly motivated particle for cold dark matter is the axion. Highly motivated is because if the axion is a fundamental particle that exists, it explains a lot of other things about physics we don't understand.
I see. So
that's why it is, and it's an elementary particle. It's hypothetical. It's postulated by theory.
Yeah.
So, according to the theory, which may or may not be right, the axion is predicted to convert into a photon in the presence of a magnetic field with the frequency given by the axion mass. And so this has been known for a long time, and more than 25 years ago, people in Berkeley, and also they worked at the Lawrence Livermore lab, came to see me and they said, John, we have ideas about how to find this, but we need a much, much quieter amplifier than anything that currently exists. And I said, can you make an amplifier for us that works at very high frequencies that is very, very sensitive? I said, well, I'm not sure. I'm not sure if I can, but if you send me some money, I'll work on it. So we did, and we worked out how to make a very sensitive squid amplifier. Mm-hmm. So this is a field that has blossomed, and there are many other institutions involved now. But in particular, there's one called the axion dark matter experiment. The X is the second letter in the word experiment. Mm-hmm. And this is now at the University of Washington in Seattle. It was originally at the Lawrence Livermore lab, but for highly political reasons, it was moved to Seattle.
I see.
And as I mentioned, the axion conversion to photon is predicted to take place in a magnetic field. So this copper cylinder at the bottom here, it's a hollow cylinder, is immersed into a cryostat at very, very low temperatures, in which there's a superconducting solenoid that gives you a very high field. Mm-hmm. And so if this is the axion may not exist, right? So it's a high gamble, but quite a few millions of dollars have been invested in it by the federal government. But anyway, if the photons are produced, then it's the squid-based amplifiers that make it possible to detect them.
Wow.
And all I can say is the search continues. And there are long reasons I won't get into why it can take a long time. But anyway, that's the experiment. You can see it's quite complicated. And this cavity is at the bottom, and then there's all kinds of squid amplifiers in all the stuff at the top.
Yeah. In general, how big are squids about, or how can we see them? Just
general. So if you go back to this picture here, so in the early days, this is 500 microns. So from side to side, from here to here is about 1 millimeter. Now, today they can be 100 times smaller than that. And it just depends on the application and the frequency you want to work it at, and all kinds of stuff that if you solve enough calculus, you can figure out as accurately as you like. And all the theory is, you know, the noise in the device and the limits to the device, and all these effects are worked out in great detail.
I see.
Yeah.
Then on the copper cavity big thing is like the squids are just all over the entire device.
They're above it
They're above it. I
because
see.
they have wires that come out of the. You don't want the squids to disturb all the magnetic fields oscillating in the cavity.
I see.
And also the high fields in the cavity would destroy the superconductivity. So
Oh wow.
all above here, all in this region here, you have all these squid packages and lots of wiring and all transformers and all kinds of stuff.
Oh wow.
Yeah.
Yeah.
So anyway, that's the first thing I wanted to talk about. The other thing was I wanted to say a little bit about searching for dark energy. And that means searching for, I mentioned that the other big puzzle, in fact, the biggest thing in the universe that's not understood is dark energy. And so one of the theories is that if you have clusters of galaxies, now galaxies are huge, but clusters of galaxies are unimaginably huge.
Yeah.
Right? I mean, they're out there in the universe somewhere. And here is an image of a galaxy cluster. All these big blobs here are clusters.
Wow.
Right? Yeah. So the idea is that if you could really figure out the density and the position of these clusters, and it would take thousands of them, you could actually start to come up, you could imagine working out a theory for dark energy. So that's
Dark energy. Wow.
Yeah. So the notion is if you could just find enough of these galaxy clusters, say 1,000, then you know, the theorists, I don't know how to do that by any way, but there are people who claim they do. So there are now many telescopes around the world looking for these. And it turns out that the visible light from these galaxies is very, very feeble. Most of the energy is in X-rays.
I see.
But it turns out that there are these very clever techniques that I certainly didn't work out that enable you to find these clusters in the far infrared, which frequencies around 2 millimeters of wavelength. And I mean, again, there's a lot of theory behind how that's done, but it's very well understood. And so this must have been in the early 2000s. One of my colleagues, Paul Richards, he came to see me and he said, you know, we really need to improve the speed with which we can read out our telescopes for exactly this kind of application. And he said, do you think you could give that some thought? And I said, well, you know, give me a week or 2 or 3. And I did. I figured out how to increase the speed of the readout by a very large factor.
Oh, wow.
Make it much, much simpler. And so that's a technique that's now used on the Berkeley telescope and on many others. And here's a photograph of this particular telescope. And because you need a very clear atmosphere, it's actually on the Antarctica.
Wow.
Altitude of 9,500 feet. And this dish here with someone running around in it is 10 meters across, about 33 meters across. And it says here, I'm sorry, I should use my pointer. It works around 2 millimeters. And one of the collaborators who sent me these photographs actually at the
Mhm.
University of Chicago. And SPT means South Pole Telescope 3G, it's third generation. And
I see.
and it has 24,000 squids doing the readout with this
Wow.
technique that I worked out. So
Yeah.
yeah, so
Do
it's
you, with the squids here in the South Pole Telescope, do you kind of like measure the magnetic fields?
no,
Mm.
no, you actually, there's a detector that if it
Mhm.
receives um, a photon at this wavelength, it converts it into a voltage.
Oh, and that also uses squids.
Yeah. And it's actually it's a superconducting sensor. TES means transition edge sensor.
I see.
And I mean, it's again, it's all understood incredibly well, but it produces a voltage.
Mhm. Wow. Mm. Yeah. And so it can read the pictures really, really fast.
Oh, yes, yes. And with huge sensitivity.
Yeah.
And
Wow.
I think to date, this and other, I think just even this one telescope has now discovered about 1,000 galaxy clusters.
Which
And
means we could find the equation from
well,
that.
I think there are people who are trying to figure it out. Yes. Yeah.
I see.
So again, it's very much driven by squids.
Yeah. Wow.
And then the final thing, I'm sorry, I'm taking a great deal of time, but anyway,
No, don't worry.
yeah. So the last thing is, I just wanted to say a few words about ultra low field magnetic resonance imaging. And I don't know if you've ever been in an MRI machine.
No.
And but anyway, it's a very important, very successful clinical instrument. And I think last time I looked it up, there were about 30,000 systems around the world. And they typically work now at either 1.5 or 3 Tesla. And they typically cost about $2 million. But it's a very
Wow.
successful technique. But I got to asking the question, um, what if we reduce the field by a factor of 10,000 to say 150 microtesla? Could we still obtain magnetic resonance images? And if so, might they be better in some way? And so in collaboration with one of my colleagues in the chemistry department, Alex Pines, we started to sort of work on this. And here is now an early version of an ultra low field MRI system imaging the brain.
I
And
see.
it's working at 100, 150 microtesla. So as promised, it's about 4 orders of magnitude smaller.
Mhm.
And the question is, what advantage does it have? And one, in fact, the principal advantage is that it has much better contrast between different tissues.
I
And for
see.
example, it's quite difficult with conventional MRI to image cancer, it turns out. But it turns out with this ultra low field, you get a very, very good contrast. And we've published papers on that and
Mhm.
to show that you indeed do get this much better contrast. And it's potentially much less expensive. And as I'll come to after, during the commercial part of my talk, it's actually being commercialized now.
I see.
Yeah.
Yeah. Is the reason why it has much better contrast between the different tissues,
Yeah.
because like our cells have magnetic fields, so the smaller, like they can detect the magnetic fields, just the clearer that is.
That's a very good suggestion. It turns out that it's a somewhat different reason.
Oh, I see.
But because the field is lower, the frequency of the MRI is much lower.
Hmm.
And the frequency of the MRI, and this is part of the reason why we got into this, is much closer to the frequency of cells. So cells
Oh, I
have
see.
these inherent relaxation times, which gives them a characteristic frequency.
I see. Yeah,
Yes, yeah.
that makes sense.
Okay, we're getting on.
Yeah. So maybe you could talk about a little bit of the various commercial applications of squids and how they're used in today's world.
Yes, yeah.
Okay.
So I picked three or four ideas. So
Okay.
I think the most widely used squid system commercially is this one here, which is the made by Quantum Design, which is a company in San Diego, and it's called the Physical Properties Measurement System, PPMS, and
Mm.
it's used to measure practically everything you can think of: magnetic things, electrical things, thermal properties. It's used to measure everything from blood samples to the properties of high transition temperature superconductors and things in between. And there are more than 1,000 used worldwide.
I
And
see.
it's been made huge contributions to measurement in labs around the world. And
Mm.
I think that if people would think if you had a physics department without one of these, you didn't have a very good physics department. we have several in Berkeley.
Berkeley. Wow.
So that's my first example. Another one is in geophysics, and I didn't mention it before, but quite early on in my time here, I got involved in making new ways of doing geophysics, and in particular, looking for properties under the Earth's surface.
Mm.
And at the time, we were looking for geothermal energy. And this was a project that was actually driven by President Jimmy Carter. And he told the Department of Energy to spend money to look for geothermal energy. And we actually worked out a very good way to do it.
Wow.
But other people, looked at this technique and they came up with their own ways of doing it. And this is a technique from Australia. And this is the Center for, I've forgotten what CSIRO stands for. It's the anyway. It's like NIST. It's the equivalent of NIST in the United States.
I see.
And this is their system when it's not very much out looking for silver somewhere in Australia, and the squids here in liquid nitrogen, which works on the surface, and then they pulse the ground and they look for the signals that come back. And these are squid amplifiers, and this is the battery box. It's very simple, and it's been hugely successful. And last time I talked to Kathy, who I know very well, she said that they discovered more than $10 billion of mineral deposits.
Wow.
Yeah.
So the squids in the liquid nitrogen
Yes.
help with this.
Yes, that's right. I mean, most of these ultra-sensitive squids work at in liquid helium temperatures, which 4 Kelvin and often much below that, because you get the best sensitivities. But one thing we also worked on in the early 1990s, when these so-called high transition temperature squids or high temperature superconductors were discovered, we made squids. And the point is that liquid nitrogen is much, much easier to use in a remote area because it boils away much more slowly. So things like geophysics you would now do with high transition temperature squids.
Oh, wow.
Yeah. So anyway, and here's another example, also in Australia. It's the Cannington silver mine. So it's predicted to have $2 billion worth of silver in it. It's the biggest known deposit in the world. And you can see that there's practically a village there where all the people working on it. And that was all discovered with this squid-based technology.
Oh, wow. And so they've built this entire thing around it so that they can just find the deposits.
Yeah. And once they found it, they had to mine it. So I think all these people are mostly involved in the mining
Wow.
And then one of my favorite applications is magnetoencephalography, MEG.
Mhm.
And this is a system to measure signals from the magnetic signals from the human brain. And last time I looked at this, I think there were about 125 such systems in use around the world. This is an invention that certainly wasn't made by us, but it enables one with incredible sensitivity to see what's going on in the brain.
Mhm.
And one important little point is that you might wonder what this sort of huge circular thing is. It's so that the patient can lie down flat. So they can tip this whole thing so they lie down flat. And the reason to do that is kind of intriguing. That turns out if you're sitting up and you lie down, your brain moves 2 or 3 millimeters. Yes.
Oh, wow.
And since conventional MRI systems have you lying down flat, if you want to compare the signals from the brain from this machine with something in MRI, you better lie down flat. So they figured out how to do that.
Oh, wow.
And in that kind of system, there are no fewer than 306 squid channels. And I won't go through the details, but it's cooled to 4 Kelvin, and it has to be in a very magnetically shielded room because it's looking for these tiny signals.
Yeah.
It looks in 2 different ways. Your brain, as you sit there listening to me, your brain is putting out unbelievable amount of magnetic stuff.
Wow.
But also I can stimulate it. So I
Yeah.
could flash lights in your eyes, and that would enable your brain to respond, and I could see if your brain is working properly. So, and again, there are many systems, but many applications of this. And I said that they're spontaneous and stimulated, but one of the things that they can do, let's see, did I? No. One of the things that they can do is to look at the signals coming from sources around the brain tumor.
I
And so
see.
that means that you can do the surgery and you can go into the brain in a way that won't damage anything else. So you don't want to have your brain tumor removed, but you can't walk or you can't see. So this has been hugely successful, and this is all done in Finland in that technique. But also I've listed a few other things: recovery from stroke, traumatic brain injury, football players, car accidents, post-traumatic stress disorder, Alzheimer's, autism, dyslexia. So there are all kinds of things done with these squid-based systems.
I see. And so with like the pre-surgical mapping of brain tumors, they just like map it out and then they're able to maybe like project it so that the surgeons know where it is?
So that's right. So they plot it all up, and that's why you want to be able to coordinate with the MRI,
I see.
because the MRI tells you where the tumor is, and the MEG tells you where not to go in. And so they
I
can find a
see.
way around all the important parts of the brain function.
Yeah, that makes sense.
Yeah.
And then they can also detect where Alzheimer's might be as well?
Well, there are all kinds of things. Yes. Yes. Because what they would find is that where you have Alzheimer's, this part of the brain isn't producing much in the way of signals. And for
Oh,
example, the part part of the brain that has memory.
mm. Yeah, the hippocampus doesn't have
Yeah.
like doesn't emit as much magnetic signals.
Yeah. Yeah.
I
Well, if you have Alzheimer's,
Yeah.
yes. Yeah. Yeah. And
I
also,
see.
if you have a stroke,
Okay.
fortunate enough to have a stroke, then part of the brain doesn't work anymore. And maybe that's the part that prevents you from walking.
Mm.
So they can look at the area where the stroke comes from, and they can apply external signals. They can sort of say, they could apply a little sort of, they bang on your leg, for example, in a simple-minded way, and see if the brain is responding to that.
Yeah,
And
I
they can
see.
see if you're, therefore, if it's going to respond, if it's going to recover.
Mm.
So what else do we have? Yes,
It's in popular literature.
yes. This takes 1 minute. So you've probably read books at some point in your life about Harry Potter.
Yes.
Yes, yes. And remember that there's this famous scene where the Sorting Hat decides which of Hogwarts house do you belong in.
Mhm.
There's nothing hidden in your head the Sorting Hat can't see. So try me on and I will tell you where you ought to be.
I see.
So do you wonder how that works?
Yes, please.
Well, there's a wonderful book called The Science of Harry Potter.
Oh, wow.
Yes, it's actually a fascinating book, just as part of all this, but he explains how it's all done by squids. And they convert a tiny change in his brain's magnetic field into a detectable change in voltage with a sensitivity unmatched by any other device.
And
So
then
that's how
they sort
Harry
him
Potter ends up where he ends up.
in Gryffindor. Yeah.
And then
Wow.
there's another book, you may or may not have ever come across it, called Timeline.
Mhm.
And in Timeline, in a word, people are able to be transmitted to a different world in atom by atom.
I see.
But you have to be able to have a completely accurate MRI of the
Oh,
body
yeah.
so it can be reassembled again.
Mhm.
And so he explains about MRI, and only works in a powerful magnetic field, but we don't need that. We use superconducting quantum interference devices, or SQUIDs, that are so sensitive they can measure resonance just from the Earth's magnetic field. We don't have any magnets in there. So with that assurance, you are disassembled and beamed off to another world.
Wow. Wow. Oh, okay. Do you think maybe you could talk about some exciting developments that are currently going on in terms of quantum computing or anything related to squids?
Yeah.
Okay.
So I thought I'd just pick, I mean, there are lots of things going on, but I thought I'd pick one thing that, I mean, has a lot of people hypnotized. And it's based on squids, or the development of squids. And that is to say, it's all about superconducting films and Josephson tunneling in various ways that respond to magnetic fields. And some of these devices, instead of having two junctions, might have 4 junctions or something like that. But it's all the basic same technology.
Mhm.
And as you probably know, your classical computer that we're talking to each other on, ignore the phone. The the classical computers operate with zeros and ones.
Nice. Yeah, binary.
Yeah, binary, exactly. Oh, you know very well. Yes, yes. And yeah, they work well enough. But
Mhm.
the quantum computers that are sort of under development work instead with quantum mechanical wave functions.
I see.
And the great thing about the quantum mechanical wave function is that instead of having 0, 1s and 1s, you can have essentially an infinite number of bits.
Mhm.
And that enables one to make something that is unbelievably faster and can do all kinds of things you can't do with a classical computer.
Oh, wow.
And many startup companies have been formed to work on this. And there's one in Berkeley and all over the country, and in fact all around the world.
Mhm.
And not all of the classical computers are necessarily based on superconductivity in Josephson. Some of them, for example, involve semiconductors. Some of them just use atoms. But the real advances have been made with the superconducting technology.
I
And
see.
for example, there are very large efforts at IBM and also at Google, of all places. And in both places, some of the former members of my research group are involved. And in fact, at Google, the project there was led by one of my former students, John Martinez, who claimed that they had achieved so-called quantum supremacy.
I think I read something about that, actually.
Yes,
Yeah.
yes. And so they claimed that they had built a machine that in about 200 seconds, they had performed a calculation that on the best classical computers would take 10,000 years.
Wow.
Now, this claim has been hotly disputed, and particularly by people at IBM, about whether it's actually true and how they did the comparison and all this stuff. But anyway, that's a very, very exciting field, lots of work going on. And so anyway,
I've seen those devices that are really big and then they just like stretch up to the ceiling.
yes, that's right. So you've seen the photograph from Google, for example.
Yeah,
Yes.
I think so.
And IBM is also doing very interesting things, and they've made both IBM and again Google more recently has made all these claims, and people are just trying to sort it out.
I see.
Yeah.
And then what kind of things are they trying to compute?
Well, in many ways, it's relatively simple things. But one thing that they've been cutting their teeth on is calculating the structure of complicated molecules.
Oh.
So if you have some very highly complicated organic molecule, it turns out you can't really calculate it. And so they've been trying to see if they can actually do the calculation or even predict new molecules.
I see.
Another big thing that's in the future is weather forecasting. I mean, weather forecasting, it turns out, is not always very good, as we've all noticed, but it seems that people believe that you should be able to do an infinitely better job at forecasting weather. And whether that's true or not remains to be seen.
Yeah, I have noticed that the weather app isn't as accurate.
Yes.
Yeah. Wow.
Ellie, I think I've come to the end. I've taken a great deal of your time.
No, it was really fun to learn all about the different things that you've done before and all about squids.
Yeah.
So
I just wanted to show you one last little thing. If we can we stop sharing at this point?
Oh,
I think we.
Yes.
Yeah. Okay. Yeah. So now we can see each other more easily.
Mhm.
And I just want to make the point that I've been very fortunate over the years to have many people in my research group, graduate students and postdocs, more than 100 who sort of worked on all kinds of experiments. But quite apart from that, it's a very big field. And just to give an example of this, there have been many summer schools on squids. And here you can see that there is a book on a summer school that I gave some lectures at. And this summer school can last for, it took 2 weeks, and many, many different people gave lectures. And, there were probably a couple of hundred students who made notes all the time and hopefully learned something. And I was also involved with a colleague of mine, Alex Baginski in Germany, with editing a couple of books. And so these were multi-authored by other people, but this is the Squid Handbook. And that's about the fundamentals and technology of squids and squid systems. And then the second book, which is even bigger, was on the applications of squids and squid systems.
Oh, wow.
So you can see it's a very big field of endeavor. And the Squid Handbook, the 2 volumes, is about 1,000 pages, and
Wow.
full of calculus.
Calculus.
Not to mention multivariable calculus.
Yeah.
Yeah.
Do you use multivariable calculus in a lot in your research?
Um, Sometimes I do. Very often what we do is we'll calculate something. We'll calculate the properties of a squid of particular dimensions.
Mhm.
And that, it turns out, you can do with single variable calculus. But then you start to play games. So you want to know, well, what happens if I change the inductance? Or what
I
happens
see.
if I change the size of the junctions? So then you
Wow.
can start to play these other games so that you can figure out all the different parameters that go into this.
Mhm.
And you
And
figure out the
that's where
noise properties, which is very, very important.
I see. And that's where you start using the mathematics
Yeah,
involved.
yeah,
Yeah.
yeah.
Wow. That is really interesting.